So in this video we're going to be looking at the integral from 0 to infinity of the square root of x divided by x squared plus 6x plus 8. Now this integral is quite difficult to evaluate by the usual methods. So we're going to use what's called a keyhole contour. So we're going to use the method of contour integration. I'm going to define my function f of z to be the square root of z divided by z squared plus 6z plus 8. But I'm going to have to be very careful with what I mean by the square root of z, and I'll show you what I mean in a second. So what contour am I going to use? Well, I'm going to use a contour called C. It's going to consist of a keyhole. So we're going to have a small circle in the middle and a larger circle encompassing it and a corridor connecting the two holes. So I'm going to start at this point here and I'm going to go along this corridor like that. And once I've gone along that corridor, I'm then going to go from this point all the way around this circle, which has radius r, capital R. And I'm going to call that circle gamma. And once I've reached that point, I then go back along the positive real axis, back towards this inner circle, and then I'm going to traverse this smaller circle, which I'm calling gamma, which has radius epsilon. Now, before I start doing any integration, let's just have a look at the function that I have. Well, first of all, z squared plus 6z plus 8, that's a quadratic, so I can very easily factorize that. First notice that I can factorize this in the following way. So z squared plus 6z plus 8, that's just equal to z plus 2 times z plus 4. So I'm going to have two poles at z equals minus 2 and z equals minus 4, and those are going to be simple poles, which means they're poles of multiplicity 1 or order 1. If this was z plus 2 squared times z plus 4 cubed, then that would be a pole of multiplicity 2, and this would be a pole of multiplicity 3, but in this case they both have multiplicities 1. So where are these on my Argand diagram? That's this thing. Well, I want to have a pole at z equals minus 2, so that's going to be around about here, and I want a pole at z equals minus 4, so that's going to be around about here. Now this is quite important because the way I do this integral is going to depend on my choice of epsilon and r. If epsilon is too big, then suddenly this pole is going to be outside the contour, it's going to be inside this little keyhole. And if r were to be too small, then some of my poles wouldn't even be inside the contour, because the keyhole would be this small and some of the poles wouldn't be encompassed inside. So what I want to do to make sure this works so that I can use the residue theorem is that both my poles are inside. So to do that, I'm going to have to make sure that the smaller radius epsilon is smaller than 2. So I need epsilon smaller than 2. And I need to have r greater than 4. Reason being, if r equals 4, then it would have to pass right through the pole. If r is greater than 4, then it encompasses the poles. Okay, so if we put all these things together, what do we get? So let's just form our integral. So according to our diagram, the whole contour, so the integral over the whole contour C of f of z dz, that's equal to what? Well, my starting position is here, so let me just draw a dot. So we're starting here and going here first, so that's an integral from epsilon to r. So I'm integrating, let's do this. So I'm integrating from epsilon to r of f of z dz. Once I've reached that point, I go all the way around. So I go all the way around until I reach this point. And what's that? So that's going to be an integral over capital gamma of f of z dz. Once I've reached that point, then I need to go back along the corridor, along the positive real axis in the reverse direction, and that's going to be plus the integral, not from epsilon to r, but from r to epsilon, because I'm now going backwards from r to epsilon, of f of z dz. And finally, I'm going to have an integral over this little circle, so an integral over little gamma f of z dz. So that's going to be my general approach. Let's go back for a second. So what do I want to do? Well, on the left-hand side, I've got a contour integral. I can probably use the residue theorem, but I need to discuss that a bit further. I'm going to have to maybe do some evaluation or playing around with the first integral and the third integral. And if you've seen any of my other videos on this topic, you'll notice that the second and fourth integrals will probably vanish. And I'm going to use the estimation lemma to show that as r tends to infinity and as epsilon goes to 0, so in other words, as this smaller circle shrinks to the origin and this bigger circle shrinks to expands to infinity rather, that these two integrals, the contributions from these integrals, vanish. But before I do anything else, I want to talk about this square root z. Now, I did mention that this might be a problem. So when you're taking square roots of real numbers, for instance the square root of x squared, that's very easily defined. If x happens to be a negative number, then the square root of x is not defined on the real numbers because you would have to end up with a complex number. On the other hand, what does it mean to take the square root of a complex number? So I want to take the square root of z, but z could be any point in this plane. It couldn't just be a real number. So I need to be careful what I do. So I'm going to do the following. I need to make sense of this expression root z. So what is root z? Well, first of all, root z, that's just z to the power 1/2. And I can write z to the power 1/2 like this. Z to the power 1/2 is e to the 1/2 complex logarithm of z. And by the way, here I'm just using the rule that e to the b log a is a to the power b. You might know that from pre-calculus. Okay, so now the issue is, how do I define this complex logarithm? Well, the way I define this complex logarithm will depend on the choice of contour. So the usual way you do it is like this. You might normally say, let's take complex log of z to be the log of the modulus of z plus I times the argument of z. And typically the argument of z is defined like this. It's allowed to vary between minus pi and pi. So minus pi would be less than or equal to the argument of z, and that would be less than pi. So the branch cut takes place where pi is, or where minus pi is. So usually that would mean here, along this axis. And that's the point, that's the point where the argument of any point in that line is pi or minus pi. But you might see that that contour actually passes through that line, so I need to make sure that that branch cut is in a different position. So what I'm going to do instead is I'm going to make sure that the branch cut is here. And so if the branch cut is there, then I won't have any problems because my contour never actually touches that positive real axis. So what does that mean? So instead of taking argument of z to be between minus pi and pi, I'm going to take the branch cut to be along the positive real axis. So I want 0 to be less than or equal to argument of z to be less than 2 pi. So I'm not taking this, so you can forget about this one, and we are taking this one. So that's the way I'm going to define my branch cut. So what does this mean for this? Well, that means that e to the power 1/2 log z, complex log of z, that's just equal to e to the 1/2, open brackets, log of the modulus of z plus I times the argument of z, where the argument of z is defined like that, where it varies between 0 and 2 pi. And the reason why this is important is because when we look at our integrals, we look at our integral from epsilon to r, that's not going to be the same as the negative of the third integral, because our function will be different once we've gone around the circle through an argument of 2 pi, and I'll show you that at the end. So before I start doing any integration, let's look at the contributions made by the second integral and the fourth integral. So let's look at the second integral. So I want to look at what I want to look at. I want to try and look at the integral over big gamma of f of z dz. I want to use the estimation lemma, which tells me that I can bound that in modulus and say that that's less than or equal to the length of big gamma multiplied by the maximum value of the modulus of f, where z varies along this part of the curve, gamma. Well, what is the length of gamma? Well, if I look at my diagram, gamma is this large arc here. It's a circle of radius r, well, it's almost a circle of radius r, and its circumference, if this were complete, would be 2 pi r. So what I can definitely say is that this whole thing, the length, that's got to be less than or equal to 2 pi r. So I know for certain that this is less than or equal to 2 pi r. But what about this? Well, my function f of z, let's see if I can do any bounds there. I might remind you that my function is this. So how can I find some sort of upper bound on this function? Well, let's look at the denominator first. So if I look at the modulus of z squared plus 6z plus 8, well, the reverse triangle inequality says that I can bound that from below in the following way. I can say that that's greater than or equal to the moduli of the individual terms. So that's greater than or equal to mod of z squared minus the modulus of 6 times z minus the modulus of 8. So I've just split that into the moduli of the individual terms. What is that equal to? That's equal to the mod of z all squared, because I can bring the modulus inside. That's a property of complex numbers. Minus 6 times the modulus of z, because I can take the constant out of the modulus sign. Minus 8, because the modulus of any real number is just that real number. Well, if this were minus 8, then the modulus would be 8. But in this case, the modulus of any positive real number is just the positive real number. But let's look at what we have here. I've got mod z squared minus 6 mod z minus 8. What can I do about these mod z's? Well, if I look at my diagram, that's here, any point on this curve, so any point here, has to satisfy the relation mod z equals capital R. Okay, so if I take the modulus of any point on big gamma, it's going to have value r, because that's how you define a circle of radius r in the complex plane. So for instance, if it were a circle of radius 1, it would be mod z equals 1. So what I can do here is I can actually replace this with r squared minus 6r minus 8. Okay, so that takes care of the denominator, because if I take, hang on a second, if I were to take reciprocals of both sides, then I can take the reciprocals of both sides and then flip the direction of the inequality. So this would be 1 divided by mod z squared plus 6z plus 8, and that's going to be less than or equal to 1 over r squared minus 6r minus 8. And I'm going to use that in just a second. So that deals with the numerator. What about the denominator? So that deals with the denominator rather. What about the numerator? Well, square root of z, that's, as we just discussed, z to the 1/2, which is e to the 1/2 complex log of z. And I want to take moduli of that. So I want a modulus of root z, just like this. Well, using my definition of log z, that's just the modulus of e to the power 1/2, open brackets, log of the modulus of z plus I times the argument of z. And that's all in modulus. Okay, and that's equal to what? Well, that's equal to the modulus of e to the 1/2 log z times the modulus of e to the power 1/2 I arg z. I've just split up the powers and split up the modulus. Okay, what do we notice here? Well, in the second term, this should be mod z. In the second term, I've got e to the power 1/2 I arg z. Well, the argument of z is always a real number. In fact, it's a number that's going to be between 0 and 2 pi. And a half is obviously a real number. So I've got e to the power of I times a real number. And if you remember, if I have e to the power it, and I want to take the modulus of that, then that's just equal to 1, as long as t is a real number. So that's true for all t a real number. If t were complex, on the other hand, that wouldn't be the case, because I could take, let's say, t equals I, and I'd have e to the power of I squared, which is e to the power minus 1, and that definitely doesn't have modulus 1. And the reason this is true, you can recall the fact that e to the ix is cos x plus I sine x, and that traces out a unit circle. So we can therefore use this fact in the following way. We've got e to the power 1/2 iarg z. This is of the form e to the it, where t is a half arg z, and a half arg z is always a real number, so I can safely say that that's equal to 1. So I can basically forget about that term. What about the first term? So I'm left with e to the power 1/2 log of the modulus of z, and the modulus of z is just r, so that's mod e to the 1/2 log r, or yep, that's correct. And what can I do now? Well, r is a real number, and I've got e to the power 1/2 log r, but that's just the same as r to the power 1/2. And r is a positive real number, and in fact r is greater than 4, as per my assumptions, and that's just equal to the modulus of the square root of r. But this is always going to be a positive number, so I can completely forget about the modulus signs, so that's just the square root of r. So putting this all together, what do I get? Well, I find that the absolute value of the integral of f of z over big gamma, that's going to be less than or equal to the length of big gamma, which was 2 pi r, times the maximum value. Well, I know that the maximum value is bounded above by what? Well, I had the square root of z, so let's just write it out again. So I want the maximum value, where z belongs to gamma, of modulus of square root z, all over modulus of z squared plus 6z plus 8. And we established that this was less than or equal to 2 pi r, that's just this term, times what? Well, root z, that was just equal to root r. And in the denominator, we showed that 1 divided by modulus of this thing is just less than or equal to 1 divided by 1 over r squared minus 6r minus 8. And that's equal to 2 pi r times r to the 3 over 2, all divided by r squared minus 6r minus 8. Now, in the numerator, I've got r to the power 3 over 2, and in the denominator, I've got r squared. So I've got a polynomial in the denominator whose degree is greater than the degree of the polynomial in the numerator, because 2 is greater than 3 over 2. So what does that mean? Well, I want to take r, I want to let r go to infinity. So I want to let the radius of this big arc gamma go out to infinity. Well, when that happens, this denominator is going to get very, very big, and it's going to get bigger at a much faster rate than r to the power 3 over 2. And that always happens when the power is bigger than the power of the denominator of the numerator. So if this were r cubed and this were r to the power 4, this wouldn't work because you'd have 3, which is less than 4. But because 2 is greater than 3 over 2, this thing just goes to 0 as r goes to infinity, and that's because the denominator is a quadratic which approaches infinity much faster than r to the power 3 over 2, which is not a quadratic. It has degree which is 3 over 2, which is less than that of a quadratic. So therefore, the contribution by that integral, which is this one, so this is going to go to 0 as r tends to infinity. So that takes care of that integral. Now we can deal with the integral of little gamma. And what's that? That's going to be basically the same idea. So if I can just get this to scroll down. So what about the integral over little gamma of f of z dz? Well, as usual, that's going to be bounded above according to the estimation lemma by the length of little gamma multiplied by the maximum value of f of z, where z varies along, where z is just a point on this curve gamma, little gamma that is. Well, the length of gamma, well, if I look at my diagram again, little gamma is this little circle here, and it has radius epsilon. And as usual, this is not quite a complete circle, but whatever its radius is, it's going to be less than 2 pi epsilon, because if this were complete like this, so if I just complete this, if it were complete, this circle would have radius 2 pi epsilon. So whatever the radius of this circle actually is at the moment, it's going to be less than 2 pi epsilon. So if I just do that here, so this is going to be less than or equal to 2 pi epsilon. Now let's deal with the maximum of this function. So I want the maximum of root z over z squared plus 6z plus 8 bounded in modulus. So I know from before that by the reverse triangle inequality, mod z squared plus 6z plus 8 is greater than or equal to mod z all squared minus 6 mod z minus 8. And this time on my curve, I'm not going to have mod z equals r, but I'm going to have mod z equals epsilon. Okay, so if I just replace every instance of mod z with epsilon, I get this. I just get epsilon squared minus 6 epsilon minus 8. So if I take reciprocal of both sides, I'm just going to get 1 over this is less than or equal to 1 over this. Okay, and what about root z? Well, for root z, as usual, that's going to be e to the power 1/2 log of the modulus of z plus iarg z, just like that. And I want to take modulus, or moduli, and that's going to be e to the 1/2 log of the modulus of z multiplied by e to the 1/2 iarg z. And as previously discussed, this term is equal to 1 because e to the it is, well, the absolute value of e to the it is 1 for any real value of t, and half arg z is certainly a real value. And what about this term? Well, for this term, I'm going to have mod of e to the 1/2 log epsilon, because mod z equals epsilon. But half log e to the 1/2 log epsilon is just modulus of the square root of epsilon. And that's just the square root of epsilon, because epsilon is just some positive real number. And the square root of epsilon will obviously be positive as well. So what can I say? That tells me that square root over, the absolute value of the integral of f of z dz taken over this part of the curve, that's less than or equal to 2 pi epsilon, that's the length, multiplied by the maximum value of f of z, and that's going to be root epsilon, all divided by epsilon squared, minus 6 epsilon minus 8. And what happens as epsilon tends to 0? Well, as epsilon tends to 0, I'm going to get what? Well, epsilon root epsilon, that's just going to go to 0. So this whole thing, so it's a different color. So this whole thing, that's going to go to 0 as epsilon tends to 0. This term is going to go to 0. That term is going to go to 0, and I'm going to be left with minus 8. So this is going to go to essentially 0 divided by minus 8, but 0 divided by anything, apart from 0 that is just 0, as epsilon tends to 0. So what we've shown is that both integrals taken over the arcs, so that's this big arc and this little arc, both of the contributions by those integrals are going to be equal to 0 in the limit. So this integral is going to go to 0 as epsilon tends to 0. Well, what do I have left? Now I've got this integral on the left, this contour integral, is equal to the integral of f from epsilon to r, and then from r to epsilon. So what can I do about that? Well, I'm actually going to look at this integral first, the integral from r to epsilon. Let's see if I can do something about that. So the integral from r to epsilon of f of z dz, that's just equal to the integral from r to epsilon. Well, what's my definition of f? That's the square root of z divided by z squared plus 6z plus 8 dz. And using my definition of the square root of z, using my branch cut, that's the integral from r to epsilon of e to the 1/2 log So log of the modulus of z plus iarg z dz, and I need to divide by this polynomial, just like that. And what can I say now? Well, if I look at where I am at this point on the curve, so if when I was integrating from epsilon to r, I was first starting out going along this direction, and this is basically hugging the positive real axis. So at any point along this corridor, along this this straight line segment rather, the argument is at any point on this line is going to be 0, because the angle it makes to the positive real axis is 0, as r tends to infinity, as an epsilon tends to 0. But when I go all the way around, so once I've traced all the way around like this, once I've done that, I've gone through an angle of 2 pi. So now when I'm integrating back over, all of the points along this curve make an argument of 2 pi with the positive real axis. So I'm not going to have the same value of f of z. F of z is going to be a different function. And this is why it's important to consider the impacts of the branch cut, because you're going to end up with a slightly different function. So I'm going to end up with what? The integral from r to epsilon of e to the power 1/2 log of the modulus of z plus I arg z, but as we've just established, arg z in this case is 2 pi. So I've got I times 2 pi, all divided by z squared plus 6z plus 8 dz. Okay, and if I split the numerator up, that's just equal to the integral from r to epsilon of e to the 1/2 log of the modulus of z times what? Well, I've got e to the power 1/2 I 2 pi. A half times 2 pi is just pi, so I've got e to the I pi divided by z squared plus 6z plus 8 dz. Well, as you probably all know, the famous identity now comes in handy, because e to the I pi is equal to -1. That's the famous identity, one of the most beautiful identities in mathematics, because it combines the transcendental numbers e, pi, and the imaginary unit I to make this beautiful identity here. And what does that let us do? Well, it lets us basically get rid of this term and put a minus sign in front of the integral. So that's equal to minus the integral from r to epsilon of e to the 1/2 log of the modulus of z dz, all divided by z squared plus 6z plus 8. Okay, and what is that? Well, if I swap the limits, then I introduce a negative sign. But once I introduce a negative sign again, that cancels out with the negative sign that's currently here. So what I end up getting is the integral from r to epsilon, but e to the 1/2 log z, well, that's just the square root of z divided by z squared plus 6z plus 8 dz. So what I've ended up getting is the same integral as my first integral. So if you look back here, that's right here, what I've ended up showing is that this integral, so this integral, is equal to this integral right here. So what I can basically do is basically bunch them up. So now I've got, what do I have now? Well, let's just write it out. Well, now what I have is the integral of f of z dz over my contour c. That's equal to 2 times what? Well, I want the limit as epsilon goes to 0 and as r goes to infinity. So once that happens, I'm going to end up with the integral from 0 to infinity of the square root of x, all divided by x squared plus 6x plus 8 dx. So if we divide both sides by 2, I think you see where this is going, then I can show that the integral that I want to evaluate, that's this thing I'm writing right now, that's just going to depend on the value of this integral. It's going to be the contour integral over c of f of z dz. So I can find out this integral just by using the residue theorem on this integral. Well, if you remember, I could factorize the denominator as x plus 2 times x plus 4. So if I just do that, that's x plus 2 times x plus 4. So there's going to be poles at, so simple poles of order 1 at z equals minus 2 and z equals minus 4. So now I just need to calculate the residues at each of these poles. Then I'm going to add them together and multiply them by 2 pi I. So let's do that. So the residue of f of z at z equals minus 2, what's that? Well, by definition of the residue, it's a simple pole of order 1, so I don't need to find any derivatives. That's just the limit as z approaches minus 2 of z minus minus 2, which is z plus 2, times f of z, which is root z over z plus 2, z plus 4. I've just factorized the denominator here. And I can cancel out a factor of z plus 2 from the numerator and the denominator. So this thing goes to 0, that thing goes to 0. Or, well, it goes to 1 is probably a better way of saying that. And that's equal to the limit as z approaches minus 2 of the square root of z, all divided by z plus 4. Now I'm again going to use my definition of the square root of z, and that's going to be the limit as z approaches minus 2 of e to the 1/2 complex logarithm of z, all divided by z plus 4. And I'm now just going to substitute z equals minus 2 into this function. What do I get? Well, I'm going to get e to the power of 1/2 open brackets log of the modulus of minus 2 plus I times the argument of minus 2, all divided by minus 2 plus 4. I'm just replacing z with minus 2. Okay, and what is that? Well, the modulus of minus 2 is 2. So that's e to the power 1/2 log of 2 times e to the 1/2 I times the argument of minus 2. And that's all divided by minus 2 plus 4, which is just 2. So I've dealt with modulus of minus 2. What about the argument of minus 2? Well, minus 2, if I just go back to my argon diagram, minus 2 is this point right here. So that's minus 2. And minus 2 makes an angle of 180 degrees with the positive real axis, or pi radians. So the argument of minus 2 is pi. So if I go down, it's right here. Keep jumping all over the place. There we go. So this is in fact just equal to e to the 1/2 log 2 e to the 1/2 I times pi, which is e to the I pi over 2, all divided by 2. Well, what is e to the I pi over 2? Well, I know that e to the ix is cos x plus I sin x, so e to the I pi over 2, what is that? That is the cosine of pi over 2 plus I times the sine of pi over 2. And the cosine of pi over 2, well, that's just 0. The cosine of 90 degrees is 0. And the sine of pi over 2 is 1. The sine of 90 degrees is 1. So this whole thing is just equal to 0 plus I times 1, which is I, which is quite a nice result. It's a useful result to remember. So that whole thing, what do I want to write? So the residue at z equals minus 2 of f of z, that's just equal to, what do I have? Well, I've got I times e to the 1/2 log 2 divided by 2. And what is that? Well, e to the 1/2 log 2, that's just another way of saying root 2. So that's I root 2 all divided by 2. So that's the residue at z equals minus 2. Likewise, the residue at z equals minus 4 is going to follow in exactly the same way. So the residue at z equals minus 4 of f of z, that's equal to the limit as z approaches minus 4 of z minus minus 4, which is z plus 4, times f of z, and my function f of z is just defined to be root z, divided by z plus 2 times z plus 4. Remember, I factorized the denominator in advance, and I can cancel out, just as in the previous residue calculation, I can cancel out z plus 4 here and z plus 4 there to leave me with the limit as z approaches minus 4 of root z over z plus 2. So what do I do now? I'm going to use my definition of root z for complex variable z, and that's equal to the limit as z approaches minus 4 of e to the power 1/2 complex log of z, which is just a log of the modulus of z plus I times the argument of z, all divided by z plus 2. So now I'm going to plug in z equals minus 4, and what do I get? I get e to the 1/2 log of minus 4 plus I times the argument of minus 4, all divided by minus 4 plus 2. And that's equal to what? Well, as usual, I can split up the exponential. E to the x plus y is just e to the x times e to the y. So that's e to the power 1/2 log, well, the absolute value of minus 4 was just 4, so that's e to the 1/2 log 4, times e to the 1/2 I argument of minus 4, all divided by minus 4 plus 2 is just minus 2. Well, just as before, e to the 1/2 log 4 is just 4 to the power 1/2. E to the 1/2 I argument of minus 4. Argument of minus 4 is pi, because minus 4 is located on the negative real axis, and that makes an angle of pi with the positive real axis. So that's e to the 1/2, well, let's write it like this, e to the I pi over 2, all divided by minus 2. Well, 4 to the power 1/2 is just the square root of 4, and that's just 2. E to the I pi over 2, as we established, is I, and we divide that by minus 2. And what is that? Well, 2 divided by 2 is 1, so that's just minus I. Minus I. Okay, so the residue, where is it gone? The first residue was I root 2 over 2, and the second residue was minus I. So therefore, putting it all together, the integral from 0 to infinity of root x all divided by x squared plus 6x plus 8, that's equal to, we showed that all the other integrals vanished, and the first and the third integrals combined into one, integral over my contour C of f of z dz, and by the residue theorem, that is 1/2 times 2 pi I times the sum of the residues. Well, the first residue was what? Was I root 2 over 2, I root 2 over 2, plus the second residue, which was just minus I, minus I. Well, now I've got a factor of I outside and a factor of I inside the bracket, so that's just 1/2 times 2 pi I times I times root 2 over 2 minus 1. Well, a half times 2 is just 1, so that's pi. I times I is minus 1, so I've got a minus sign here. And the terms inside the brackets just remain exactly the same. And if I want to neaten things up a bit, I could write this. I could take the minus sign inside the brackets and say that that's equal to pi 1 minus root 2 over 2. So therefore, the integral from 0 to infinity of this function, root x over x squared plus 6x plus 8, is equal to this very nice number here, pi times 1 minus root 2 over 2, which is a very beautiful result. So that's the end of this video. Thanks for watching. If you liked my content, if you liked the video today, then make sure you leave a like, comment and subscribe to my channel. And if you want to see more content just like this, then stay tuned for more. Thank you.